Thank you for joining us in this video. We are going to look at the work with the calculator for solving sequences and series. And this is the part of the practice set for Module 2B. So here we're told to expand the finite series and then hence state the sum. So remember, if we're working with the series, I'm going to have my terms separated by a plus sign. I do have my calculator available to help, and there's a variety of ways that I could work with this. All right, so one way, if I wanted to get term by term, I could do it by hand, or I could come in and say, hey, let me add a sequence and say my sequence is given by my 2n plus 1. All right, so I have 2n plus 1, and I could say, well, what are going to be my values? And I have my values for n equals 1, 2, 3. So if I'm going to expand this finite series, this is going to be equal to 3 plus 5 plus 7 plus 9 plus 11. All right, so I have when I is 1, when I is 2, when I is 3, when I is 4, and when I is 5, and I want that summation. All right, then I can either do that sum on my own, or I could use my calculator to help me with the sum. Go to my toolbox. My summations happen to be under calculus, and I have the summation from 1 to 5 of 2 times my counter plus 1. And that summation is 35. All right. How would I do it for the next one? Like I said, I could come over to my sequences and adjust my sequence, and now my sequence is going to be my counter squared plus 1, and I come down to display my values, and I know that this summation is actually going to start at 0, so I might, and it's going to end at 4, so I'm going to go ahead and come in and say, okay, well, what do I have with starting at 0? And it's like, it's not defined. So we do have to think a little bit. Well, if k is 0, I'm going to have 0 plus 1, which is 1. So this is going to be 1 plus 2 plus 5 plus 10 plus 17. Right now, wait a second. I want all the way to k is 4, and so that works for k is 4. And that summation, I could either do it by hand, or once again, I could come over to my calculation, go to my toolbox, right? In the calculus toolbox, come to the summation. Now I have the summation from 0 to 4. I want to be careful with that. My counter squared plus 1, and that gives me a summation of 35 as well by chance. Right? There is an interesting property about why these two have the same sum, but I'll save that for another time. Okay. So if we look at number 5, we want to expand each of these series and state the sum. All right, we want to expand the series and state the sum. And like I said, you don't necessarily need to have a calculator to do these, but for students that like to have the calculator, we can come in and make that adjustment. All right, so we can say, hey, let's come over and look at our sequence. And now for this one, we have 24 minus 3 times my counter. Okay, and let me display my values starting at 1. And so that's going to be 21 plus 18 plus 15 plus 12 plus 9 plus 6. All right, so that's the summation from n is equal to 1 to 6. And if I find that sum, all right, we come back to our calculation, and we could always arrow over and copy a previous piece if we want to do it that way. And we can say, hey, we've got the summation of 24 minus 3 times my counter, right? And my counter is starting at 1 and ending at 6. And that summation happens to be 81. Okay. Then for number 4, right? We should recognize that we're going to get the same issue that we're starting at x is equal to 0, but that's okay. We know what to do for that situation. So we have our sequence, right, is going to be parentheses, -1 raised to my counter all over my counter plus 1. So that -1 raised to the counter, I know is going to create my alternating series. And if I want to display my values, I do have to remember about being careful with the calculator and saying, do I really need my calculator to do this? Because I could have very easily, if I start at 0, I'm going to have 1 over 1, right? And then if x is equal to 1, I'm going to have, right, instead of a plus, it's going to be a minus 1 over 2. And then -1 to the second power is going to be positive 1 over 3. Right? Then -1 to the third power is going to be negative 1 over 4. And then -1 to the fourth power over 4 plus 1, so plus 1 over 5. Right? So we see -1/2, 1/3, -1/4, positive 1/5. We see these summations. That's my summation. Right? And the total sum, if I add all of that together, once again, we said we can go to our calculation, come to our toolbox, go to calculus, find our sum, and we'll have our summation, right, going from 0 to 4, and I have division. The numerator is going to be -1 raised to my counter, and the denominator is going to be my counter plus 1. Find that summation, and it gives me this value, right? And if I want to have that as an exact value, I could certainly do that in a slightly different way and say, hey, if I want that as an exact value, that's 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. All right, and we'll see that that is 47 over 60, which is approximately 0.783. All right, but we prefer exact answers if we can. All right, so that's expanding some series. All right, now writing a series using sigma notation, then state the value. So I'm going to need to figure out how many terms I have for each one of these. So I'll start with my summation notation. Right, so if I look at what I seem to have here, it seems to be that I'm going to have 3 times my counter, let my counter start at 1 and end at 9, and it's 1 over that. Then I can just use my calculator to solve. All right, for this one over here, what seems to be happening seems to be that I'm multiplying by 3 each time. So that's going to be a summation, right? And I can say, hey, from n equals 1, and I can say that's going to be 3 to the nth power, right? And I just need to figure out 729. What power is that of 3? Well, 729 divided by 3 is 243. Divided by 3 is 81. So that means I'm going to go to 6 because 3 to the 6th power is 729. So I have just that summation, and I'm going to use my calculator to make that determination. I come to the toolbox, right, go to the summation, and I'll work backwards here. So 1 to 6 of 3 raised to the counter, and that gives me a value of 1092. And we'll show you how to find that value in a different way in a future lesson. And then we have the summation from 1 to 9 of 1 divided by 3 times my counter. And that gives me approximately, what is that? 0.942989418. Right? Which, of course, if you're going to do 3 decimal places, you could say it's 0.943 if I'm rounding. All right? We continue. All right? We want to write another summation using sigma notation and evaluate. And we get the hint for the first one that we have an alternating series. So now I can deal with my alternating series by having a -1 raised to a power. Given that I start with a positive number, if I'm going to start my counter at 1 and take my counter to 20, because it seems to be 1 squared, 2 squared, 3 squared, 4 squared, then I'm going to have my counter plus 1 so that I get an even number and a positive alternating series when I work for the first part. Okay, and if we do this particular work, then we're going to have 1 over that counter squared, and come to my calculator, right? I have the counter from 1 to 20 of parentheses -1 raised to the counter plus 1, and then I'm going to have 1 over that counter squared. And if I look at that summation is approximately 0.8213. All right, to 3 decimal places, 0.8213 would give me 4 decimal places. All right, now this alternating series is a special alternating series, and it's similar to the alternating series that we have up here in number 5, where 5b gets referred to as an alternating harmonic series, 1 minus 1/2 plus 1/3 minus 1/4, and we notice that the denominators are just increasing by 1, whereas in this one we have the alternating harmonic series, but we're squaring each term, and this ends up being called a p-series and something that gets used later on, or in other words, a power series. But this happens to be working with a power of 2 in the denominator. All right. If I look to number 7b, I want to write summation notation or sigma notation. Easiest is to start my counter at 1. I notice that each time I'm going up by 2, so that's going to be 2n plus 3. So I get 5 as my first term. And then I have to figure out, well, how many terms to get to 23? That would be 10 terms, because 2 times 10 is 20. All right, which gets me 23. Use my calculator. Start the counter at 1, take the counter to 10, and it is of 2 times the counter plus 3, and that gives me 140. Okay, so almost there through this particular work. Right, we want the fourth partial sum, S sub 4, and the total sum, given what we have for our summation. Okay, so let's look at how this will work. Our fourth partial sum, we go to our summation. We're going to go from 1 to 4, right? And it is of 6 all over 10 raised to my counter, right? And so that gives me the fourth partial sum. The sum of the first 4 terms is going to be 0.6666, right? But my infinite sum, if I come over and I say, well, what if instead of going to 1, right, what if instead I went to 40? Right, I see that repeating, 0.6667, and I said, okay, well, what if instead I went to 400? And I see that same piece, and then we're like, oh, wait a second, 0.6 repeating, that's going to be 2/3, right? If I look to part B, right, my fourth partial sum, I have to be careful. I'm starting at 0, so the fourth partial sum is going to be with the top being at 3. And so then I have 27 divided by 100 raised to the, not the third, right, raised to the counter power. And that is going to give me, right, the sum of the first 4 terms is going to be 27.272727. And if I look to have this summation go to 300, I see that that's going to be repeating, right? And I can think, well, how do I have 27 as a repeating decimal? How might I be able to deal with that? And there are a number of ways, right? And I'll give you this approach. Let's say I do 27 divided by 99. We know this is 27 divided by 99 gives that repeating pattern. 1 divided by 9, right? 2 divided by 9, 13 divided by 99, right? What if I had 13 divided by 999, right? Or 130 divided by 999, or 132 divided by 999, right? So we can look towards where our pattern repeats, but of course 27 divided by 99 is one approach that I could use for that, which gets me down to 3 out of 11. And I can say, well, what's 3 times 20, what is 11 times 27? That is 297. So I could say that exactly 297 divided by 11, right? And we could double check that. 297 divided by 11, right, is 27. But we're like, oh, wait a second, I need the plus 3. So that's going to be 300 divided by 11 once we check our work, and that gets us 27.27 repeating. All right, so that's an interesting property once again, that if I divide by 9, I'll repeat 1 decimal place. If I divide by 99, I'll repeat 2 decimal places. And if I divide by 999, I'll repeat 3 decimal places. There's other patterns, but that's what we'll deal with for now. All right, so last questions. The first 5 terms of our recursively defined sequence. One approach is to use our sequences, right? But we're going to, we're going to say we're going to add a sequence, and we're going to have a first order recursive definition, right? Where my my next term is based on the current term times 2. So I'm going to say 2 times, right, the current term plus 1. And where that first term is equal to -8. And I could come and display the values. And I say, okay, well, my first term is -8. Then I'm going to separate with a comma because I have a sequence. And then what does it say? 2 times that number plus 1, so -15. 2 times that number plus 1, -29. 2 times that number plus 1, -57. 2 times that number plus 1, -113. And those are the first 5 terms. Okay. If I look at part B, that recursive definition is going to be let's come back, right? That recursive definition is going to be a second order because we have 2 terms to start off with, right? And we say, okay, well, what do I have? I have, if I look to this, I got to be careful. I say that my term in 2 terms is going to be based on the term just before it, right? Plus the term before that. But if I look at what I have in this case, I would be able to say that, hey, b sub k plus 2 is going to be equal to b sub k, right, minus b sub k plus 1. All right, if I replace k with k plus 2, that's k plus 2, k plus 2 minus 2, k plus 2 minus 1. So I have to be aware of how to work with this. And so that means that I need to have my first term, right, be the b sub my counter. And then I have to have minus, and you're going to come over here to VAR, to my sequences, and I'll say, oh, okay, hey, I have v sub, right, then I have my counter plus 1, right? And so I need to make sure that I put that in correctly, where my first term is 2, and my second term is -3. I need to make sure I put that in, and then display my values. And I can say, hey, what's my first value going to be? Right? Well, I don't want it for my u sub n, I want v sub n. So my first value is 2. My second value is -3. How do I get to the next value? It's going to be the difference between 2 and -3. So 2 minus -3, that's 5. -3 minus 5, that's -8. 5 minus -8, that's 13. So notice I have this interesting alternating series, right, that is found in a slightly different way, but it does have an alternating series to it. But we just happen to define it recursively, and we want 5 terms, so 1, 2, 3, 4, 5 terms. So there we are, working with sequences and series with the calculator, finding patterns. It's a different area of mathematics that some find interesting, some find a little bit more difficult, but always make sure you practice, make sure you ask questions. Thank you for your time.